Okay, so David, the floor is yours after the short introduction.
We can make this smaller. Good. Hi, everyone. Thanks a lot for the nice introduction. That actually was most that I wanted to say during my first slide. So what I'm going to present is
Good night, everybody.
As Andreas mentioned, I'm David Kaltenbrunner. I'm working at MPE together with Chandri and Frank. And what I'm going to present to you is the work on creating a catalog of high-mass X-ray binaries that we did in the LMC using eROSITA data, more precisely the first eROSITA scan. Right. So, and if you don't know much about high-mass X-ray binaries or the LMC, don't worry, I'm going to explain this. So, first of all, sorry. Yeah, that works. What are high-mass X-ray binaries? High-mass X-ray binaries are binaries that consist of a high-mass star, as the name suggests, and a compact object. Compact object is then accreting matter from the high-mass star and thus is radiating X-rays. The most common type of those are so-called BE X-ray binaries. BE X-ray binaries are B or O stars that show emission lines in H alpha and H beta, which is caused by this decretion disk that you can see in this image here. So there's a disk around the star caused by rapid rotation, and this disk is redder and emits in H alpha and H beta. And then if the compact object gets close to this disk, it accretes more matter. So this is the first type. And then the second type of high-mass X-ray binaries is if we have a supergiant instead of the BE star. And there we then either have low slope overflow if the system is sufficiently close, or we can also have accretion from the stellar wind of the supergiant. So that's the summary of this. We either have BE or supergiant sources. And in BE sources, what is very typical is that we have a specific pattern of outbursts. There either are type 1 or type 2 outbursts, and those type 1 outbursts are if the object goes into the disk and then every orbit you see a flash. But there is also the possibility that a large amount of matter is gathered by the neutron star or the black hole, which then causes it to be bright over several orbits. This is what you see here. So this large outburst here is the so-called type 2 outburst. The way that we identify those systems particularly is we have an X-ray source and then a BE star. So we have a star which shows those emission lines where usually there should be absorption lines in the stellar spectrum. What is typical for those systems, they are relatively faint, and then during the outbursts, they brighten up by several orders of magnitude. Then supergiant systems, if we have a low slope overflow system, so a closed system, they are very bright constantly. Those are at around 10 to the 36 or 10 to the 37 hertz per second. They are one of the brightest objects inside of the galaxy, except for in EGN. Right, and then why are those systems interesting? So for one, we have extreme physics at those. We have a compact object with very high magnetic fields, very high gravitation, and very high temperatures. And we observe those quite closely because of the interaction between the two systems. This is the one thing. But then what's especially interesting for me personally, those systems only happen to live in a certain age range, because you need to have a supergiant star or a high-mass star, which doesn't live that long, but at the same time, you have to have a compact object, so you have an old star. And since you have this binary system, they can't live that long. Typically, this is at the order of 10 to probably 50 or 100 mega years. Right. Then, now we know why we want to study high-mass X-ray binaries. Why do we want to do this in the LMC? Generally, the Magellanic Clouds are the closest star-forming galaxies in next to the Milky Way. And the small Magellanic Cloud has already been studied in great detail. Large Magellanic Cloud, not that much yet, because of two major reasons. The first one, there have been older studies with eROSITA, for example. But eROSITA had the problem that it was not that sensitive, and also the positional accuracy was not that high, which you can see in this image here. You see, so the blobs that you see, you only see the brightest ones, and also they are quite fuzzy. So it's kind of difficult to associate the optical counterpart with the X-ray counterpart, what we need to do for our high-mass X-ray bindings. Of course, have been newer studies, XMM, but then the second issue comes into place. The Large Magellanic Cloud is approximately 10 by 10 degrees in the sky. And if that doesn't say anything to you, this is approximately 20 by 20 meters. So this is really huge. And as you see, there's been a lot of XMM pointings, and still only the central region, those of the highest star formation, have been studied. The SMC has been covered entirely with XMM. And this is now where eROSITA comes into play. eROSITA, as Andreas already mentioned, has been scanning the entire sky. And those scans overlapped at the north and the south ecliptic pole. So at the bottom, you then see the south ecliptic pole, which is the one that's interesting for us, because the LMC is quite close to this, which means that the scans, eROSITA scanned the LMC a lot more than the rest of the sky. So we have quite deep exposures, can do interesting studies. And what this resulted in for eROS-1 was this. And isn't this beautiful? Like, you can see the entire LMC, it's so beautiful here. Good. So, what we do with eROSITA? We use the source catalog, and then we use point sources. So the extent needs to be 0, because high-mass X-ray binaries are supposed to be point source. Then, even though we have a lot of sources inside of the LMC that we see in here, still the majority of the point sources that we see are AGN, and we need to get rid of those. The way that we do this is, for one, we use objects of relatively low positional uncertainty. We use an upper limit of 9.8 arc segments for one signaling, which is the 95 percentile. Then we also use objects where the detection likelihood is relatively high. So for the entire eROS-1 catalog, they use a factor of 6. But since we do have a lot of hot gas here in this region, as you can see, there's a bit more spurious detections. So what we do is we use a detection likelihood threshold of 20%. This is for one, that we get a lot of spurious sources, and also we want to be able to properly fit the X-ray spectrum, because then we can differentiate between X-ray binaries and HGN. And then the last thing, we already, before doing any matching, get rid of all the known, so the securely known AGN, both with known redshifts, and also of known foreground stars, because they can also be foreground force. Good. So this is what we do with the X-rays. The next step is then that we correlate with the optical counterpart of the high-mass star. What we use here is especially 2 catalogs for color stability, and then a third one for position. The first one that we use is the Magellanic Cloud photometric survey. This is a 4-band photometric catalog. It's in UPV and light. And what we do is we select a certain region that you can see in red on this plot here, which is the tip of the main sequence, and this is where the high-mass stars are. Yeah. And the second catalog that we use is an infrared catalog, where you see the Magellanic Cloud survey, which is a 3-band near-infrared catalog. And this is not that much for selecting the high-mass stars themselves, but rather to get rid of traditional AGN, because what is very nicely seen in infrared colors is the difference between the stars. Because AGN would lie somewhere here, or even above. So those are the typical selection regions for generator. And our sample is nicely set. And then lastly, what we use is also the information on the proper motion. So we only select objects where the optical counterpart matches the proper motion of the galaxy. This really starts more precisely the ER3. Good. So by matching those catalogs, we have a sample of candidates. But now we want to understand how good all those candidates are, how secure we are about all of those matches. And the way that we do this is by assigning specific flags depending on measurements that we did and the results that we got, and then assign confidence classes according to those. And this is one of the main parts of the paper that we see. And let's go through this one by one. The first one is relatively simple. This is the class of the secure homosexual binaries. So we know that they are homosexual binaries either because we know the spin period of the neutron star or because of other things. For example, for a black hole binary, we won't find the spin period, of course, but still we know that it's an extra. The next class is also fairly certain objects. Here we don't have a spin period yet, but we do have an X-ray spectrum that matches this of either a neutron star or a super soft source, which will then be a white dwarf. And we have the optical spectrum, which shows us the emission rates. So the X-ray spectrum from eROSITA typically looks like this. What you can see in the plot in black is the entire spectrum. In blue, you see the background, and in yellow is the source itself. And then if the power law index is below 1, we can quite certainly say that it is not EPG, but it's that it is transition. So this is one of the positive effects. Then for the emission lines, as already mentioned, we have H alpha and H beta. If they show emission, we set this correct. So what we did for most of our new candidates was to take LCO Floyd's spectrum, which is a telescope in Australia, if I remember correctly. Right, and then we fitted the lights and checked if it's emission or absorption. For some of the objects, we also used salt. This we did especially for interesting cases. Good. Then the next class is not that certain anymore. We still have an X-ray spectrum that matches this of what we expect. But then we don't necessarily have an emission line, but this decretion disk can also show an infrared axis. And this can be seen in two different ways. So what we did here, what a collaborator, Julia Rubensteiner, did for us here, was that she used the Vizier data and then fitted an SED to the entire data there. And, or no, see, she fitted it up to 10 microns, so around here, with stellar models. And then if you see, like in this plot here, an axis of the data, so of the colored data points compared to the model expectation, this is this infrared axis. This again is caused by this. Another way of seeing the infrared axis is also in infrared colors. And here we used the 2000 SAGE surveys. And yeah, if there is a specific name, this already in literature has been used as a measure for VE systems. Good. Then next is this is now not a spectrum or anything, but instead, if we find an orbital period in orbit data, so we have orbit data for the entire catalog, and if we find a period that looks somewhat like that of an orbit, then we use this flag here. This does not necessarily mean that we really have a high-mass X-ray binary, because it was found that these stars sometimes also show similar periods, but still, it is a good indicator. So this would then look like this. What is generally typical in those systems is that one does see quite a lot of variability overall, but then also one can see periodic behavior. And if we did find a period, we also put this in the paper, of course, to give an estimate for the over the period of systems. Now, the last confidence class of what we call the good candidates is now this here. If we find similar high variability in X-rays, then this is also an indication for being homosexual binaries, because typically AGN are a bit less variable. I will show you this in the second plot. So the first one is, this is how it does often look like. So we have something like an outburst in one of the eROS scans. All the other eROS scans is fainter, or it can also be that within eROS scans it changes quite a lot. So if we find within eROSITA a variability of a factor of 100 or more, this we see as an indication for an electric binary. We also did this for long-term X-ray variability. Here we used the upper limit server. And if we there find a variability of about 30, we also put a positive flag. And here you can see the distribution of variabilities in the eROS data. So we used a set of secure AGN and our sample of X-ray binaries and our candidate sample. So class 1 is the X-ray binaries, and classes 2 to 6 are the green ones. And you can see that the AGN only go up to around 100, and then there is nothing anymore. And in fact, I also had to cut off some objects that are at much, much higher values, simply because that would not be good otherwise. Good. And then this is what we end up. So we find out of the 59 previously known homosexual binaries, 28, which is not that surprising because homosexual binaries are variable. And those 31 that are not seen in eROS1 also show luminosities that are below the detection threshold of eROSITA. So this is just variability and sensitivity at that scene. What is completely new is that we find 21 objects that have never been studied or seen before that are completely new because of eROSITA. Those are the yellow lines. And what you can see is that they are especially distributed here in the outer regions, so exactly where we would expect it, because XMM, if you remember, was seen especially this part, this part. So exactly where there have not been any older studies, we do find new candidates. Then also out of the known candidates, we find 4. And then now compared to ROSAT, we have much better positional accuracy. So what was possible is to find back the ROSAT sources and then reject them because they do not match the position of a Planck star. So those are the 5 which are also actually one thing that I want to draw your attention to are those green contours on the plot. Those indicate how long the exposure over eROS1 was. So it does change quite a lot. In this region here is exactly the SCP. Then as we go further away, it does go down fast. And then as it approaches the SMC, which is somewhere here, it is approximately at where it is in the rest of the space. So really only in that answer we can do this kind of study. Good. Then how does this look like if we look at the entire population? First, looking at the counterpart, so at the B stars or the M stars, and looking at the color plot, V minus I versus Q color, so this is a B red color. In the SMC, the population both of the underlying B stars, which are those gray dots, as well as those in binaries, the circles, they are quite compact, so they don't spread out We can see this in the population of microsexual binaries at SMC. Nearly all of them are EE plus neutron star. There's, I think, one single supergiant, and that's basically it. In comparison, in the LMC, even though we have less X-ray binaries overall, we do find a much wider spread. We also see this in the population then. We have more, I think it is a total of 7 supergiant X-ray binaries, even though we only have around half of the total system's characteristics. And this is seen both in the binaries as well as in the population. Then another interesting thing is the first step in the direction of the star formation rate or star formation history. As I mentioned, the HMXB binaries are very closely linked to this. And the way that one can roughly look at this is by looking at the luminosity function. Because what Grimm et al. 2003 found in nearby galaxies is that the normalization, so generally that all of them are distributed approximately according to a power law in all of the galaxies, but then the normalization is quite tightly coupled to the star formation rate in the galaxy. And this is what we did here. So we looked at the normalization of either confidence class 1, so the highly secure ones, or classes 1 to 5, and then checked the normalization and compared it to what they find in the Grimm et al. Paper. And what we do find is that the star formation rate that we get by using this as an estimate is within a factor of 2 of other measurements, like HMXB measurements. And this is within exactly the uncertainties that they find in their estimate. So that's great. Now, the next step, what I'm currently working on, is that we do not look at the current star formation rates, because HMXB binaries have already lived around 5 megayears in order for one of the stars to go supernova and a neutron star, but that we look at the star formation history. The way that we do this is we use the Harris and Zaritsky catalog of star formation history in the LMC, and then if we compare positions of HMXB binaries on the bottom right with the same number of random positions, is that we find that at high H's, so around here, the two are quite similar. So here we have around 0.1, and here you can also see it's around 0.1. This is good because it should not have any influence on the HMXB binaries. But then if we look at H's of around 10 megayears to 50 megayears, which is from here to here, there we see a huge spike for the HMXB binary positions. This is exactly what we expect. And this is what I'm working on together with Andreas this past week and this week, especially where we want to, for one, show this. So we already can. And the next step is then to get the efficiency to understand how many HMXB binaries are formed per stellar mass. All right. So in principle, I'm at my summary, but since we still have a little bit of time, if you're still interested, I could show you 2 specific types of systems that we find in the. So the first one that is quite interesting are E plus white dwarf systems, not the typical E plus neutron star, but it's the white dwarf companions. And we could find 3 of them in our sample, or we find 3 candidates. The way that they look like is they are very, very soft, so super soft objects. And you can see this in the spectrum. I forgot to show you the difference. So we have to go a little bit back. Sorry for that. This spectrum here. So this is the standard spectrum. We look from 0.2 to 5 kV. And you see the source is visible in pretty much the entire band. And then in comparison, here, we only go up to 2 kV, and the source already is close to negligible at 1 kV. So it really only has photons in the very lowest energies. This is the super soft one. population synthesis models, they show that there should be approximately 7 times as many plus white dwarf systems compared to plus neutron stars. But not many have been found, and it's not really clear why. It might be a sensitivity issue, but we're not sure. So this is really great that we find this. We do find strong H alpha line for all 3 systems for the counterparts, which means we definitely have P stars. And then generally they are, they basically are 2 different systems. First one does show a strong outburst in eROS1. This was the one where I showed you the light curve earlier, so where you saw huge volume in eROS1 and the rest was undetected. And the other 2 show basically a constant volume. And if one does a spectral fit with a black body spectrum, what this then looks like is that the one outburst, we see the entire white dwarf surface during this time. Otherwise, we don't see anything. And the other 2 look like we have a hotspot of around 50 kilometer in size. All of them are around 50 to 100 EVs when we fit it. But super soft sources could, in principle, also be black holes. So what we did was to check for this. So there's 2 possible ways that it could show, that a black hole could show. Either we have a super soft spectrum, which looks like disk black body model, or we have a power, and we tested both. For the disk black body model, what we did was we allowed masses between 10 divided by 3 and 30 solar masses. And then we put, with this, put upper limits on temperature, upper and lower limits on the temperature, and on the normalization, by assuming that the black hole is non-spinning. And that's it. And what we find with this is that the one system, so the one on the right, actually all 3 of them do not work well for the disk black body, even the 2 fainter ones. For the power law model, there will be assumed power indices of up to 4. Typically, they are up to around 3, but we allowed it to be a little bit larger. And what we found was for the brighter system, we can definitely exclude this. For the fainter ones, it could in principle match. But the thing is that the power index wants to go to a value of 4 or even higher. So it doesn't really look like it anymore. So what we say is that we can quite securely exclude or say that it is not black holes in all 3 systems. So what we have is in fact black holes. Right, and then the second very interesting type of objects are so-called supergiant fast X-ray transients. Those are supergiant systems where one sees very short flares. So they are at the order of hundreds of seconds, maybe thousands of seconds, where one has those short, bright bursts, like here. Oops, sorry. Here and here, where the luminosity increases by a factor of at least 100 typically. And we do have 2 already known systems in the LMC. Those have been published. We do find both of them. And then we also find a new candidate which shows exactly this behavior. So those flares that you can find see here are approximately a factor of 200. And we studied the system in more detail then. So what we did was to look at salt spectra, if those change over the orbit. And also we looked at where the flares lie when looking at the orbital period from orbit. And the latter one you can see in this bottom picture. And it's quite interesting that they lie at approximately the same phase. This is seen in some systems, but not in all of them. Yeah, but still. this is a new candidate that we find, and it's very interesting. It would be great to study it in more detail, but for this we can use that spectrum. Then I am now really at my summary. So we created this new catalog of X-ray binaries, where we used infrared, optical, and X-ray information for flags for confidence classes. We did the luminosity function as a first step towards the star formation rate, star formation history. And yeah, what's very interesting is that our population is more diverse than that as you see. And the next project is then explain you with the star formation history. And if you're interested in the catalog, in the position of the objects and some of the properties, even before the paper comes out, you can check the QR code in the top right. There you will get to the eROS1 catalog page, and there one of the catalogs is this. So you can play around with a bit of interest. Now I'm happy to take any questions. Thank you.
Thank you very much, David. So, questions?
Question about one comment. And with the very narrow energy band that we're using, 2.5 kV, it's very difficult to constrain the power. Our no expect to contribute above 10 kV or 50. So using that as a criteria to rule out whether you want a black hole or not, it's a bit because you said you can have a photon index of 4, but you are so expecting up to 2 kV. And then constrain the power to because it's the soft photonization. So you have soft photons that are photonized opposed to intensive.
In principle, yes. But if you look at the spectrum, you do see that the source falls up so quickly that this is the only part we have. So
yeah, but this value, for example, data 4, if you have this spectrum up to 20 kV, it's value that you get the photon index of 4, or it's not 4.
But if we have more than 2 kV, we won't see more of the source. The blue spectrum is the back, the yellow is the source. So even if we go to higher energies.
Yeah, but you said not in this case, but use the power low to rule out a black hole.
Yes.
That's what I understand.
Yes.
You said that you have messages on values. All I'm saying is just that you know that with such a narrow balance complicated. You want to fit a power law, you will fit, but maybe just the last 3 points is giving you the power. Anyway, the second question, the question is some years ago, people were doing SMC, I don't know, South claim that they have a bimodal distribution of the spin fields. Do you see anything in that?
We don't, but we are not sure if this is because of the log statistics. We do have logless systems in CC, or if it does not exist. So, other question?
The first one is about the sample selection. You mentioned that you use infrared diagnosis, but at the same time you mentioned something about the infrared itself that you expect from the. So I was wondering if the infrared diagnostic, which exclude ETNs, has any sort of overlap with the infrared diagnostic for select PH3 line. So I don't know if even if the bands are the same.
So in principle, if we would just use stellar spectra to get those selection, the selection region, this might be a problem. But what we do instead is that we use the distribution of known X-ray binaries and then with this get the selection region. And then all the candidates have to lie within the similar region as the nodes.
And the second question has to do with the loss function that you developed. Given that Tiras is flux limits, in this reverse function, so do you correct the difference?
Yes,
This
we
is the
did.
problem.
So we first tried to get the luminosity from the spectral fitting, but then exactly this correction makes it possible, because the sensitivity depends on the count rate in the catalog, and this is kind of hard to correlate to the luminosity that we get from fitting, because depending on the power law, the count rate will change for the same luminosity. So what we now did instead here is we use an ECF or a power law index of 1, a correlation function between the luminosity and the count rate. So basically just a factor to get from the count rate in the catalog to a luminosity estimate. And then we are able to correct for the sensitivity and impedance. And where one does see this is in approximately those 3 bins, so they are shifted a little bit up from this correction. This is already the corrected one. We do not publish the uncorrected.
Yeah.
What's the mistake this dash plus libraries? Do you know? I don't know if you, but the most common progression channels of this stuff, or if you have paper.
I can give you a paper for the prediction of the number, but the information channel
More question?
One last thing. Yes, can you go to the project to show the star formation?
This one?
Can you elaborate how to produce this plot from the data? It's very nice place.
So the way that we produce these plots are relatively simple because we already have the data for like the LMC is split up in a grid by the Harrison-Savitsky 2009 paper, and then in each individual bin they have basically this distribution. So they have a value for a given metallicity and an uncertainty for each value. And what we do is that we sum up or average over all the positions where minus extra binaries are for the bottom right one. And for this one, we take the same number of positions, but randomly distributed as a comparison. This one looks very similar to if you look at the entire LMC. So if you just sum up all the individual bins, which is to be expected, and this one is. So there you see this huge spike, and this is not visible in the average. And if you're also interested in how they got the plots, like raw data, kind of, what they do is they use the MCPS survey and then use collection kind of isochrones, and then within certain H bins, they then fit the entire the distribution of stars inside of the H.
Let me ask one or two questions. One is follow-up to Pablo's question. Do you find any new parcels from the eROSITA survey?
So we do not find any spin periods with eROSITA, but there are some objects where follow-up XMM observations show positions in periods. But those have already been published by Planck.
So these are known objects. So there are no new
Yes.
objects. And the other question is, you mentioned at some point that you look at the optical variability from the Oculus survey, if I'm not mistaken. How did you deal with the non-secular variability of the because there might be some periodic signal due to the orbital period, but these objects are notorious for non-periodic variability.
So you mean basically
Exactly.
so this is what Frank is working on, and he's using a script by Lena Treiber and Georgios Vasilopoulos. They have done a similar study of variability in the SMC, and what they do is that I think they have 2 or 3 different ways of getting the basically mean value here, which they can subtract, and then do this. So what Frank then does is that he does this in several steps and different different versions, and he checks if any of them shows a significant signal for something further.
Okay. And are there many objects for which you can get orbital periods based on that?
Yes.
I believe.
I can't tell you by memory. I can show you, but it is quite objects where we can find periods.
Okay. Because this will be very interesting compared with SMC because of the different formation periods.
Yeah. Actually, 2 objects where I know that we do find orbital periods are the BE white dwarf candidate, this one that I showed. For this, I don't know the period we find anymore. But also the SFXT, where we find an orbital period of around 6.2 days. Yeah, which is actually seen on this. So this is the high magnitude that we get from OPA.
Okay, thank you. So, is there any other question? Let's thank David again.